Okay, let's get started. It's 9:05. Hello all, welcome to the May 2022 community call for Apache Hudi. My name is Sudha. I'm a Apache Hudi PMC member. Can you go to the next slide, Sudha? Yeah, today's agenda is like we will go through short community updates, and then we have two exciting talks, one from Siva and one from Vinoth. And then we'll open up for questions. Community updates. Last month, we had 62 authors contributing to all the PRs that went in. We had merged 123 pull requests and closed 67 issues. And next slide, please. And then we had 0.11 release. So please check out that and let us know what do you think. We passed 1,900 Slack users and 3,200 GitHub stars. We have one new RFC. This RFC is exciting. It talks about introducing new table APIs and config changes to make it improve the usability further. So please check out the RFC and provide any feedbacks that you have. Next slide, please. And these are the ways that you can engage with our community. Probably Slack is the easiest one. You can just hop on Slack and then say hi to fellow users and start asking questions, file issues in GitHub. We do have mailing lists for deeper questions or any discussions that require consensus or with other Hudi users. And also, please, we always welcome doc contributions and technical code contributions. If you see something in the docs, please flag us. We'll be happy to fix that. If you have time, we'll also be more than happy to take in contributions from you. So without much delays, I'll pass it on to Siva for walking us over the multi-modal index. Siva comes from Onehouse. He's a software engineer in Onehouse, and he's our own Apache Hudi PMC who has worked along in this feature along with others. So take it on, Siva.
Okay, cool. Thanks, Sudha. Hey, hi, folks. This is Sivabalan Narayanan here. As Sudha mentioned, I'm a long time in Apache Hudi. I'm a PMC, and I'm a software engineer in Onehouse. Today, we're going to discuss about multi-modal indexing in Apache Hudi. So, yeah, first we'll talk what's an index in general, and then we can dive into multi-modal index, a brief intro about multi-modal index, what's the purpose it solves, and then we can get into the requirements and some of the guarantees around it. We can briefly talk over the design, how we have designed the multi-modal index in Apache Hudi. And then we will also talk about an interesting feature that's an async indexing that comes along with the multi-modal index framework. In this section, finally, we can talk about some performance measurements we are able to glean out of the one of the new partitions that we added. And then in the end, we can discuss more planned work around multi-modal indexing and some of the future work we have in the scope. So indexing is a widely employed in database systems such as RDBMS data warehouses to locate information quickly. This is pretty similar to how in an index page at the end of the book helps you locate information. In data systems, such indexes are used to reduce your I/O costs and commonly used to improve your query performance by a large factor. There are very well-known index techniques widely used in the industry with databases like hash-based index, primary, secondary, bitmap, and so on. Most data systems actually come a lot of indexes out of the box, but there are some which also lets users add some of the indexes based on their necessity. So Hoodie has uniquely supported indexing capabilities from its inception to speed up upserts on your lakehouse. Indexes in Hoodie is used to locate incoming records during writes. Hoodie has quite a few out-of-the-box indexes like Bloom filter-based index, simple index, and edge-based index. So each of these index caters to a different workload. Typically in a data lake space, you will find like largely you could bucketize or categorize workloads into 3 different buckets. First one is a fact table. which is used to store factual information like trips in case of any transportation service or orders in case of e-commerce and so on. Most updates happens to the last few partitions. These are typically date partition, and so it happens to the last few partitions, and a very small tail spanning folder partitions. The second one is a dimension table where it has very high dimensional data. For example, users or merchants information was stored here. Updates are pretty small, but it's spread across the entire table. So third category is like an event log from Kafka. As you could imagine, these are immutable and are occasional deletes as well. Sometimes it could come with deduping requirement as well. So the merge cost for these reads or writes, it's actually will be determined whether you have such an index or not. If not for indexes, each delta increments has to be merged with all existing data files, as you could see from on the left-hand side of the figure. But with indexes, the merge cost is drastically reduced and improves your write or read cost. In terms of Hoodie, to be precise, the write cost is actually reduced with COW, and it's a read cost with the MOR, because that's where the merging happens. Now, scale of your data in your lakes has grown to like 100x or even 1000x compared to traditional databases and warehouses. And since indexing is proven to benefit your read and write performances in databases, Hoodie is introducing a generalized indexing subsystem called Multi-Modal Index with 0.11 release of Apache Hudi. This is expected to bring drastic performance gains to your lakes. Essentially, this framework provides different types of indexes to for your tables in Lakehouse to assist in improving your read and write costs at different points in time. This is designed to be engine agnostic and storage agnostic so that everyone can benefit without much overhead. As you could see, Hoodie supports a lot of query engines here, from Spark to Flink, Hive, Presto, Trino. So the core of the multimodal index is actually built within Hoodie, Hoodie's core code base, and some integration is required for every query engine. So the core metadata table in Hoodie is actually rethought and redesigned to realize the multimodal index for Hoodie. Each partition in metadata table is meant to provide different benefits for users. With 0.11, we already have 3 different partitions, namely files, columns, charts, and Bloom filter, which we might dive in later in the section. So let's take a look at the requirements and guarantees of a multimodal index. As the scale of data in data lakes is growing ever and ever to like 100x, index itself could grow to like terabytes in size. So your index is expected to scale to terabytes of metadata. Storage and compute should be decoupled so that scaling each of them should be easier. It should be easier to plug in any new type of indexes without much overhead. You should also get self-managed services, preferably like cleaning, compaction, without much overhead, so that there is less friction in adding new type of indexes. So next requirement is around ACID transactions. Since every write now has to update both data table and metadata table, we have designed a multi-table transaction with ACID guarantees to ensure no partial writes are exposed to the readers or writers. This is very critical to get it right, because it could lead to data loss or duplicated data, which could make the entire table unusable. As seen from the previous slides, multimodal indexes are meant to boost your performance for reads and writes. So it is expected to serve faster lookups. If we get into specifics, most lookups in these indexes are needle in a haystack kind of lookup. So these indexes are expected to have faster point lookups and range reads. This is different from the typical scan-based reads, which Parquet or Avro is very known for. So we ran performance measurements across Parquet, Avro, and Hfile. Hfile is from Hbase, which is known to be performant for point lookups. So we added that as well in our measurements. And then as you could see from the figure, point lookups in Hfile could give you 10 to 100x improvement over Parquet and Avro. We took like a single file containing 10 million entries. We looked up 1 entry versus 2 and then scaled to like 100. And then we saw Hfile actually stands out tall compared to the competitors here. So we did end up choosing Hfile as underlying format for metadata table based on these experiments. So multimodal index uses the base metadata table as the foundation. As you might be aware, we are using Hoodie's MOR table as our internal metadata table for various reasons. Major reasons being faster writes and no external dependencies. We have also chosen H5 format, as we saw in the previous slide, for both data file and log files in our metadata table format layout for faster lookups. As you could see from the animation, any writes that's sent to the table is committed to the data table followed by the metadata table. Multi-table transaction ensures no partial write is exposed and partial failed data is rolled back safely. This is designed to be self-manageable in terms of table services, like cleaning, compaction, and so on. With 0.11, our multimodal index has 3 partitions or indexes for your benefits. We can take a sneak peek at each of the indexes we have. So the files partition stores information about files in your data table partitions. So information stored are like file name, size, and active state. This will assist in avoiding a lot of file system calls, such as isExist, file status, or list status in the system. In cloud storages like S3, for very large deployments, a high number of file system calls could result in throttling, and could, so such caching of file meta information in your metadata table is going to be very effective in such cases. These are also served via a central timeline server. So it's even better with centralized caching from an executor standpoint. These are indexed or keyed on partition names. And so looking up valid files for a given partition is very fast. And this is what most of the queries end up doing. So the next partition we are going to discuss is a Bloom filter partition. Hoodie's out-of-the-box Bloom filter-based index involves reading the Bloom filters from the data file footers during index lookup. In this new partition that we have added in our multimodal index framework, we are storing all these Bloom filters for every data file in a single partition in metadata table. This will avoid expensive operations like reading footers of all data files during index lookup. For example, in case of a non-partition data set, we can't avoid but touch every Bloom filter of the data files in your entire table. With 0.11, these sweeping reads are avoided, and all these information, that is Bloom filters for data files, are read from a single metadata table partition named Bloom filter, reducing the direct FS calls enormously. Also, we are also looking to avoid to load all the Bloom filters on the driver directly with this new index and metadata table. So the next partition here we have is a column stats partition. As the name signifies, these store statistics of interested columns like min-max values, total values, null counts, etc. These stats will assist in data skipping while serving your read queries. Again, keys in this partition is chosen wisely in such a manner that prefix-based read or range read is feasible. And with H5 format, these are known to be blazing fast. This will drastically reduce your I/O burden and the amount of data read from your tables. So as you could see from the figure, the cost of stats pruning with column stats partition and metadata table is on the order of number of predicated columns rather than the total number of columns in your table. So in general, the predicated columns, as you could imagine, should be on the order of range of probably 1 to 5, whereas the total number of columns in your table could be 100 or even more for larger data sets. So data skipping with column stats is expected to be more efficient in terms of the time to prune for your read queries. From our analysis, we have seen 10 to 30x improvement with read queries by enabling data skipping with Hoodie. Hoodie is proud of a feature called async indexing that comes with multimodal indexing framework. Hoodie is the first to support building out indexes without blocking any writers in your data lake or in your lakehouse landscape. This means that regular writers don't need to take a hit to initialize or bootstrap a given multimodal index with metadata table. Whenever a new index is scheduled to be built out, a new indexing action is added to your timeline. And then your asynchronous process will kickstart. It will bootstrap all your commits until time tx to your metadata table. In the meantime, if any concurrent writers are coming through, they make delta appends to your metadata partition of interest. Hoodie ensures that these partitions that is being built out is not exposed to the readers until they are fully built out without any commits, with all the commits from the data table. So during this concurrent index building, we ensure that we take lock only for a minimum granularity time, and otherwise there is no lock involved across both concurrent writers as well as async indexing. In the end, there is a catch-up phase to ensure that the async indexer doesn't miss out any comments. Let's take a moment to dive into this example as given in the figure. So let's say you have regular commits happening to your table, like T0, T1, etc. A user starts an indexing scheduled at time T4. So async index process will take all the completed commits until T4 and then start to build out your index and metadata table. Any concurrent writes, for example, T3, T5, T6, and T7 will proceed concurrently without any issues, committing to both data table and metadata table. With respect to metadata table, each of these will make delta appends to the metadata partition of interest. Again, MOR is a significant factor here. If not for MOR, all these are going to take, this design may not be feasible. So in the end, async indexer, once it is done with this work of bootstrapping or building out entire until T4, it does a catch-up phase. So for example, in this case, there could be a race condition where T2 did not make a commit to the metadata table. So the async indexer will do a catch-up and then replay the T2 commit to the metadata table. Once everything is completed and validating that everything is caught up, the async indexer will wrap up the work, complete the indexing action, and then open up the partition for serving the reads. So just to recap, async indexing is meant to initialize or bootstrap your multimodal index for your Hoodie table without blocking any of your concurrent writers. So we took the files partition or files index and metadata table and measured the performance by scaling the number of files and partition. We compared 3 different variants. First one is a direct file listing using FS calls. Second one is a file listing using a file index within Hoodie. And the third one is using the file index along with timeline server based caching of the file listing information. Timeline server is contacted by executors during the life cycle of any write. So the caching of the file information read from the metadata table is going to give us more benefits as well. As seen from the graph, direct file listing is 2 to 10x slower compared to the timeline server based file listing based on the information fetched from the metadata table. In fact, for a very large table, for example, we measured like for non-partition data set with like 1 million files, direct file listing could not even complete after 3 to 4 minutes. With timeline server based, we were able to get it around 20 seconds or so. So these numbers are showing the benefits only for the files partition for file listing information. With column stats, as I told you before, for data skipping, we are able to see 10 to 30x improvement on your query performances. We have a blog coming out soon around this, but in the interest of time, we are just covering the files partition in this talk. Yeah, final slide here. So we have a lot of planned work around the multimodal index work stream in the next release or 2. We have a record level index planned to store record to file level mapping. Actually, we have a patch already out on this. So this will benefit very large tables where existing indexes could not scale beyond a point. For example, even your, let's say your index size is of order of terabytes of data. Next one is we are working on a new multimodal based Bloom index, which will leverage the Bloom filters from the metadata table instead of Bloom filters in your data table, in your data file filters. We also have plans to add more and more index types. We have an RFC out on log compaction. This will open up the ability to do a lot of small or minor compactions to compact n number of log blocks to a large log blocks without incurring a full file slice rewrite. We also have plans to decouple table services for individual partitions or indexes in the metadata table. This will give us flexibility to perform table services like compaction or cleaning for each partition or for each index at its own pace without impacting any other partitions. And that's a wrap from me on multimodal index with Apache Hudi. We also have a blog out on multimodal indexing, which you can find it on Onehouse website. Also, it's also linked in our Apache Hudi website under blog section. Open to any QA, I guess pretty much. Yeah, that's it from me. Open to QA. Or Sudha, do you usually open up the QA towards the end?
We have like 5 minutes or so. We can take questions immediately, and after 5 minutes, we can move to the end.
Okay, got it.
Thanks, Siva.
Do we have anything on the chat? No.
No. Probably I can just ask on behalf of users, I think. Siva, can you explain us how the existing Bloom filters would work with respect to the new the Bloom filter based index in point 11? Does users have to do anything, or like is that automatically taken care of? What are the differences?
So is your question how to leverage the new Bloom filter based index in the metadata table?
Yeah, and how does it differ from the existing one?
Okay, so we have certain configurations that need to turn on to leverage the new Bloom filters based out of metadata table. We might have it as part of the release highlights, what configs that you need to turn on to actually leverage it. But the basic premise is that, yeah, you should enable metadata table, which is default enabled. And then you should enable Bloom filter and column stats in the metadata table as well. Those two are by default disabled. So you need to explicitly enable them to actually leverage it. If these two are enabled, and then there is another config which can be used to enable like the new Bloom index built out of the metadata table itself. I can see if I can fetch it out in the chat history in a minute or two once I get hold of the configs. But from a user standpoint, yeah, just turning on these configs should be fine. The first ride will definitely involve like bootstrapping your entire index, but from then on, it should be good.
Sounds good. Makes sense. I think we have a question from Gatsby in chat.
So hi, thank you for your presentation. So my question is basically, I cannot use the async compaction in kind of AWS Glue because it doesn't really run on background. So I mean, when you introduce the multi-index, you said there is something called like async indexer. I'm also wondering, like, you know, maybe, I mean, is there any chance the async indexer doesn't run asynchronously, you know, in AWS Glue?
So this is a separate process in itself. I'm not sure. So when you meant async compaction doesn't run in Glue, is it like async compaction you run along with Delta Stream or continuous mode, or is it a separate async compacted job altogether? There are different ways in which.
Yeah, it is all together, just one Glue job, and then just one Glue. And then, so basically, I don't use MOR table right now because the async compaction doesn't work. I think there is some issue, GitHub issue. I mean, you and me talk about. So at the end, now I don't use MOR table because async compaction doesn't work. And then async compaction only works for a specific table. And then, you know, in order to run the async compaction with different glue job, then I have to bring up multiple glue. So I don't want that. So I'm just using COW table. So I have kind of same question when I look at the async indexer.
Okay, so yeah. I get it. Okay, so to answer your question, at least from the perspective of async indexer, this is a separate Spark submit job altogether. So I don't see a reason why this will not work. This is, as I mentioned, you need to trigger this job explicitly from a separate Spark shell or something.
Separate Spark job. Okay.
Yeah, this is a process. Yeah, this is a separate Spark submit job altogether.
Got it. I mean, does it support multiple table with one process, or is it only for one table? One process, one table, one process for multiple table.
Sagar, do you know if we can
one process per table?
Okay, yeah. As of now, it's one process per table, but we have plans to actually make it work for n number of tables within a single submission. Yeah.
Got it. Thank you very much.
Okay, thanks.
Any other questions, folks, or sounds good. I think we can start with Vinoth's presentation and then take questions in the end. So next up, we have our veteran speaker, Vinoth Govindarajan from Uber. If you remember, he presented the the BigQuery sync last time, and this time he's going to walk us through Snowflake sync of Hoodie tables. Take it away, Vinoth.
Thanks, Bernie. Yeah, hello folks. I'm going to talk about Snowflake sync today. You guys can see my screen, right?
Yes.
Okay, perfect. So today I'm going to talk about some background and motivation of why we are building this, and then I'm going to dive into implementation and design. Then, as part of this sync, what are the assets we are creating in Snowflake? I'm going to touch upon that, followed by usage and demo. Then I'll end with what are the limitations, current limitations, and the next steps on this initiative. So a little bit of background. Snowflake, most of us already know, but just for clarity, I'll just touch upon briefly. Snowflake is fully managed service, and it's a cloud data warehouse and data lake. It's used for most of the data engineering needs, and it's one of the popular out there. Snowflake currently doesn't support Apache Hudi table format, but it supports Parquet, ORC, and Avro formats for external tables. And we are going to leverage that to sync Hoodie tables, copy on write tables on querying on top of Snowflake. So when you directly query the Hoodie copy and write table on Snowflake, since copy and write maintains multiple versions, it will result in duplicate records. But by using the sync, we carefully filter only the latest snapshot so that you don't have the duplicates. And the reason we are building this is because there was some early interest from the community, and some handful of companies already exploring it. And when they try to do this without the sync feature, there is a latency delay in which they actually write the pipeline and write the data to the cloud store, and then when they sync it, they have to do a lot of manual steps in order to sync the table without causing any duplicates. And that's the reason now it is automated and part of the sync package, so that with few configs you can enable it and make it work seamlessly. Once you write the data, the next moment you can query the data in the Snowflake as well without any latencies. I'll dive into the implementation. Most of us already know how the copy on write works. The copy on write maintains multiple versions of the Parquet files, and it keeps track of which is the latest file using the Hoodie metadata layer. Without the metadata layer, if you query just the Parquet files, if you just build external tables on top of the Hoodie data files without the metadata layer, it will read all the versions of the Parquet files and it will cause duplicates. To avoid the above scenario, this proposal is to implement a Snowflake sync tool, which will use the Hoodie metadata and to know which files are the latest files, and will filter only for those Parquet files when you're querying the table, so that you can query the table without any duplicates. The sync implementation will identify the latest Parquet files for each commit file whenever you commit, and it will keep this manifest synced with the Hoodie manifest table, so that that manifest table is used for filtering out the records from the actual versions table. This feature will implement the abstract sync tool, similar to the Hive sync tool, BigQuery sync tool. It uses the same model as that of BigQuery sync for syncing the tables. So as in the high level design, we have a Hoodie writer and the Snowflake sync tool configured. Once you configure that, the Hoodie writer is going to write the files onto your cloud store, either GCS or S3 or other cloud stores. Once you have that on the cloud store, the next thing is as part of the Hoodie writer and as part of Hoodie Spark data source writer, as well as the Delta streamer, you can supply a bunch of sync classes. Either you can sync it to a Hive, BigQuery. Similarly, you can also supply the Snowflake sync tool as a class, so that it will use the Snowflake configs and it will create 3 different tables. One is the Hoodie manifest table on Snowflake, and then the Hoodie versions table, and then the Hoodie table as a view. The manifest table is going to have all the files the latest snapshot files in this table that just have one column, which is the file name, which is going to keep track of what is the latest file. This is replacing the Hoodie metadata layer and telling Snowflake that these are the files after this commit. These are the latest files. Just query these files. And using this manifest file, we are going to query the versions table by creating a view on top of it, so that when you query the view, you actually get only the latest records and not the duplicates. As part of this sync, we are going to create multiple assets in Snowflake. So for any Snowflake external table, to create that, you need to create a stage in Snowflake. So this is going to create a stage on Snowflake. After that, for schema evolution and schema inference, right now the external tables, for external tables, Snowflake is not supporting schema evolution. So for that, we need to create a custom file format and infer the schema from the data files, from the Parquet files we have. Once we infer the schema, that is also going to have the virtual columns and other things, which Snowflake needs to extract the data from the external table. Once you have that, then you use the inferred schema to create the versions table. And you have the manifest, you need to create also the manifest table, which is going to keep track of the metadata of which files are the latest. And finally, you have a Hoodie table as a view, which has the deduplicated records. So you will not query the manifest table and versions table, that those are internal. Whenever you are querying the same Hoodie table name, you will have a view, which is going to be the primary way in which you will query the table. How to use this? So in order to use that, you need a Snowflake property files. This is going to have the Snowflake's credentials and the Snowflake zone and which warehouse you are going to use, all the details. I'll show this file as well in the next slide. Then you have the storage integration. For every cloud storage integration, you need to create a storage integration, and that's one of the input parameter for this sync. Then you have the sync table name. What is the table name you want to sync? And if it is a partition table, then you need a comma separated list of partition fields. And to extract the partition, like when you are inferring the schema, the partition columns are not, it's part of the layout, so it is not being extracted. So in order to extract the partition expression, you need to say from the metadata, how would you extract the date or whatever the partition column is. If it is a multi-partition table, you will comma separated list of extract expressions. And then what is the base path for your table, which is either any of the cloud storage location. Then what is the file format, whether it is Parquet or ORC. It supports both Parquet and ORC. What is the, like, for these are the additional configs which we have. One is to use metadata, use file listing from metadata. Other is the Hive state partitioning. On the Snowflake property files, you should have the URL on where you are connecting, what is your account ID, and the username, and the private key file, and the role, warehouse, DB, and schema. This is one of the input for this here, the Snowflake property files. I'll dive into the demo. As you can see in the Snowflake, I don't have any manifest table or the versions table or the demo table. Let me dive into the code. So I have two jobs. One is the Delta Streamer job, which is going to read some data from a Kafka topic and write that into a cloud storage. Also, In the cloud store, you don't have the Hoodie demo table. So here first I'm going to generate some data. So I have I'm generating some data and putting that into Kafka. Then I'm going to trigger a delta streamer job. This is a typical delta streamer job, which I'm using creating a copy on write table on a Kafka source. And the base path here is a cloud storage, Google Cloud Storage and stock text demo. This is the target table name. And I have the Kafka properties and the schema provider. It's a file-based schema provider. Just going to take a minute to, okay. Now you can see the files in the Kafka. If you refresh, you see the demo table and a commit has been initialized. Meta table was not found, so it is just creating a metadata table. I'm running this from a Docker. The reason I have not configured the sync as part of this Delta streamer is because like the Snowflake libraries needs the Scala version 2.12, and in the Hoodie Docker demo, I have the Scala version 2.11. That's the reason I'm running this job separately. But if you're using Scala 2.12, then you can actually combine both into one. You can just supply the enable sync here and supply the Snowflake sync tool as a class, which will on committing, it will automatically going to sync the data. Now let's take a look at the files. You have a commit and you have a partition as well. Now when I need to run the sync. So here I'm just running the sync as a Java command with the same location, which is the demo location, which I just created the file, and the table name is stock text demo, and I have the Snowflake property files as well. So as part of this, it is creating a stage. Then it created a manifest. Then it created a custom file format. Then it created a demo versions, like the versions table, and it also created the view. Now, if you go to Snowflake and look at the manifest file, you'll have one manifest file. And you have in the versions, you get all the data for that table. And as you can see, right now we have only one version. So the versions has 197, and even the view will have 197 records. But if I go and add more data, so I'm going to again generate more data and create more versions. And the delta streamer job again. And if I come back here, it is going to create one more commit file. And as you can see, as part of the sync, it created a manifest file inside the .hoodie folder. Inside that, you have the latest snapshot being tracked. And this is the one which, on top of which we create a table, and that is the one which is filtering all the records for you. And this is the same manifest file we are using for BigQuery as well. So yeah, same architecture. Now, as you can see, it created one more partition. And I think the commit is complete as well. Okay, commit is complete. Now I'm going to run the sync again. After that, if you can query the versions table, you'll see more records. Right now you have 197 records. So since I added more and more records, you have 1,300 rows, and it has a lot of duplicates in the versions table. But if you query the actual stock ticks view, you have only the deduped records, 591. And this is a partition table with the partition key as date. And whenever you sync, automatically it discovers and registers new partitions. Actually, there is auto refresh mode. Whenever you create a table, you create with auto refresh. That is not being enabled for Google Cloud Storage and for external tables. But as part of the sync, we are running this. There is a command we need to run to refresh the tables, which is alter external table refresh. We are running this so that it's being refreshed always. I'll go back to the presentation. So that's all I had for the demo. And there is a PR out with the detailed instructions on how to run it. You guys can try on your own as well. So the current limitations are, currently we support only copy on write table and not merge on read tables. And we haven't tested the data files written using Flink. That is a code path which we need to test. Apart from that, it works for schema evolution and everything works here. Because we are inferring the schema every time, that works. So the next steps is to work with the community to merge the Snowflake sync PR. Then work with Snowflake team to support the custom input format. The reason we are doing all these additional tables and other things are because the Snowflake doesn't support Hoodie table format natively. Maybe we need to nudge them towards supporting that. So until then, this is the way you can query the external Hoodie tables on Snowflake, and we need to test and productionize the Flink code path. Yeah, that's all I have. Let me see if there are any questions in the chat. Okay, those are for indexing.
Hey, Vinoth, I have a question.
Yes.
I did not review your BigQuery sync patch also, so probably this is already solved. Can you go over how rollbacks are synced to these external syncs? Rollbacks in Hoodie, rollbacks or restore, all this.
Yeah, so for rollbacks and restore, whenever you do that, like if the manifest table needs to keep track of it. Whenever we run the sync tool, we are running the manifest. We are recreating the manifest file. We are looking at the timeline using the metadata API. From the timeline, we get all the latest files and update that to the .manifest file, the .manifest folder, and then run the sync methods. So every time we run the sync, the manifest will be synced first, and then the actual metadata, the actual tables will be synced.
Okay, you mean to say that whenever we run the sync, we try to fetch the latest snapshot and then
Yes.
sync only those files.
Yes, yes, yeah.
Okay, okay, got it.
So,
So if someone is having a lag in which how often they are doing the sync, that could be some mismatch.
yes, yes, yeah.
Okay.
So unless yeah, if there is the recommendation is to use the sync as part of your data streamer job or your Hoodie writer code.
Okay, got it.
If that is run async, then there is a lag. If it is not, then we are actually, it is similar to the other how Hive and Presto reads the input files. We use the same metadata layer and track the files and then update it. Yeah.
Okay, okay, got it. Yeah.
Hey, my name is Gopi. I have one question on Snowflake.
Yes.
So you said we will be creating a view, right?
Yes.
On top of Hoodie. So that means whenever we query on Snowflake, every time are we going to scan the entire table of Hoodie?
The view is just going to be on top of the Hoodie versions table. Just it is going to filter only for the files which we need. So it will be a query on top of the versions table, and it was going to filter only the deduped records.
Okay, so that means predicate push down will still work. That's what you're saying.
Yes, yes.
Okay, got it.
Any other questions?
One more question, sorry.
Yeah.
When we are thinking to release this feature officially?
So this will be part of the 0.12 release, I believe. That's the target for the in the Jira. But if you need that, once the PR is out already. Once it gets merged, maybe if you want to patch your 0.11, you can patch the 0.11 with just this one PR, then it might work. But officially, it will be part of the 0.12 release.
Okay, thank you.
Any other questions, folks?
Yeah, thanks, folks. For Thiago, question from Thiago in the chat. There is no full rewrite is required, but maybe you need to watch out for how you actually migrate your tables from pre-11 to like 0.11 Apache Hudi. So I'm pasting the release link there. So it'll go over, especially when you want to enable metadata table or any of these new partitions, something you need to watch out for. So this document will give you those details.
Okay, Siva, thank you. I think I read.
Yeah, thanks.
All right. I see some questions from Sambhav. Sambhav, I think like for this specific issue, we could defer the conversation to Slack, or you could also leverage the office hours that happen every week on Thursdays, 8 a.m. Pacific. If you have any questions related to the general roadmap or features, feel free to ask, or else we can save time for others. All right, then. Thanks, Vinoth, for walking us through the demo. It was really cool. I will end the recording and upload the video to YouTube and post it in the Slack channel. Any other questions before we close for the day? All right. Thank you. Thank you so much, folks. See you in the next month's meeting.
Okay, thanks. Thanks.
Thank you.
Thank
Thank
you.
you.